So first things first, let's actually just go ahead and define what the integral test is. The integral test is going to be the first series convergence and divergence test in which can be applied to a broad range of series. So if we just have a general series, say n equals 1 to infinity of a sub n, the big idea is going to be as long as we can integrate a function related to our series generating function, we're going to be able to figure out if this series is convergent or divergent. So in other words, what the integral test does, it puts the question of convergence and divergence of a series onto an improper integral of the continuous function analog to the series function a sub n. So what does this actually mean? So if we have this series from n equals 1 to infinity, what the integral test says is suppose f, some continuous function, it's three things: positive, continuous, and decreasing. So the function f must be positive, continuous, and decreasing. Specifically on the interval from 1 to infinity. And again, this interval is coming from the original series from where n starts and where n will end at infinity as well. So we're going from n equals 1 to n equals infinity in our series. So that's where we care about this function be having these three attributes. Okay, and we define this a sub n, this f function in the following way. We define f of n to be equal to our series function a sub n. In other words, for example, if we have a series n equals 1 to infinity of, say, n squared all over n cubed plus 1, for us, our function f of x will just be that same function, except with all the n's replaced by x's. So hopefully it doesn't look too scary when we talk about this continuous function analog to our series function. So let's actually define this series test. Our series from n equals 1 to infinity of a sub n is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. And again, where it's starting from 1 to infinity, is because that's exactly where our series function is starting from n equals 1 to infinity, or the index of our series. So another way of saying this is if from 1 to infinity f of x dx is convergent, then our original series from n equals 1 to infinity of a sub n is convergent as well. The second thing is if the improper integral from 1 to infinity of f of x dx is actually divergent, then we can automatically say that our original series from 1 to infinity of a sub n is also divergent. Okay. And to recap, a few things to note. The first thing, we define our function f of x that we're actually integrating based on our series function a sub n. The next thing is that f of x, must be three things. Number one, continuous. 2, positive. And 3, decreasing. And all of these things have to be on 1 to infinity, or basically where our index from our series starts, from n equals 1 to n equals infinity. So again, if our function f of x is those three things, we get to apply the integral test. And then based on what the improper integral does, we automatically get to say our series does the same thing. So let's quickly think about a few pros and a few cons of the integral test. A pro of this test can be applied to a lot of series. So far before this test, all we had was hopefully this series could either be geometric or maybe it's possibly telescoping, but if it was not one of those two things, we were out of luck. So again, this is the first series test that can be applied to a lot of series to test for convergence or divergence. Now let's talk about some cons. I would say the biggest con, although we can use this to test for convergence and divergence of lots of series, the con is we have to do an integral. And just on that note, as we've seen before, we've seen some integrals are tricky, or in other words, some integrals can't even be done using the methods that we've talked about so far. So that's basically what we have for integral test. It's a test that can be applied to lots of series as long as we can do the improper integral of the function that's associated with our series function. Stay tuned for some examples.